Okay, so let me just begin. So how many of you have some idea of scaling laws? Maybe I think we had covered this topic before, but do you have some kind of a very good idea of scaling laws? Some of you might be having some idea of scaling laws, right? Just give me 1 second. I'm switching this Zoom on my uh, desktop also. Then start. Okay. So feel free to interrupt me. You can unmute yourself and ask me questions, or if you want to write it on the chat window, that is also fine. Okay. Uh, okay. So let us just begin then. So today we'll be talking about scaling laws for large language models, right? And when I say what the scaling laws, let us first of all talk about the order of magnitudes of the data and the compute. So these slides have been taken from multiple sources, right? But they will be mostly talking about two very interesting papers which talk about the scaling laws and how they impact LLM training and the final performance of those LLMs. Okay, so what it says is the following. The first line says here that if suppose every day you are reading a very long book, which has maybe around 180,000 characters, 80,000 words, right? Then in your life, in your entire life, maybe whatever life, maybe on an average 70 years of your life, you are going to read almost 2 billion words, right? So this is on an average per human being if they are reading this long, very long book every day. Okay, so 2 billion words is something which is what you can read in your lifetime. Okay, but when we compare this kind of number with the kind of language models which are trained these days, very popular language models, for example GPT-3. So GPT-3 has been trained on, so this is how much? This is 2 billion, right? And this is how much? How many tokens? This is almost 300 billion. 300 billion tokens. So GPT-3 was trained on 300 billion tokens. And if I somehow kind of convert these tokens into words, so it is going to be almost 200 billion words. So almost 10x. 10x of what a human reads in his or her entire lifetime. Okay, so this is what the GPT-3 has been trained on. Okay, now let us compare this training with respect to the data sets that are available, right? So suppose the one very common popular data set that is available is called Common Crawl, which is an internet snapshot. So this has this many number of words, 10 to the power 15 number of words, right? So again, this is huge. If I compare it what we can read as a human in our entire lifetime, right? And when I talk about the English Wikipedia, so not just about the entire Wikipedia, English Wikipedia. So English Wikipedia has almost 3 billion words. Almost kind of, I would say, almost similar to what a human reads in the entire lifetime. So just somewhat more than that. Okay, so we are talking about this magnitude of data and what amount of compute is going to require to train our models. Okay, so I hope this slides just gives you the idea of how much data we are going to train our models on, right? Again, this is just a small snapshot. We are going to have even more bigger models, right? Even more bigger kind of training paradigms. We are training on even more than what we see on Common Crawl. Okay, now let us talk about transformer language models. So I hope at least in our group people know about transformer language models. What about the other people, the interns? Are you aware of the transformer language models? I shared some slides with you, some reference video lectures with you. I hope you have seen those, right? Can you confirm if you know about the transformer language models? At least the basic transformer, the encoder and the decoder ones. Okay, so okay, assuming that you know what a transformer model is, so transformer model, the kind of decoder models, if suppose we are specifically looking into, so they have these multiple layers, right? So these are kind of maybe suppose we are saying, so these are kind of 6 layers, 6 decoder layers, right? And whenever you are feeding words into them so that it predicts the next word. So the idea is that suppose you are saying my name is Mayank, and then fill in the blank, right? So the model has to fill the next word, what will come after Mayank, right? So the idea is that it has to fill maybe Singh with a very high probability. Okay, so for each word that you are going to feed to this model, you have some dimension. You are going to kind of create a vector of real numbers for that particular word, right, to represent each word. This is your D model. Okay, and this number of layers are your N layer. Fine. So if in this case N layer is equal to 6, whereas in real and in kind of the popular and the very kind of very good language models, it can even range to 96 or even more than 100. Okay, so and then D model is the length, is the dimension of the vector which is used to encode each token. Okay, so it again ranges from 512, 1024, 2048, 4096, and so and so. Sometimes it is even 20K, 30K, 32K, and so and so. Right, so that's the D model, that's the dimension of the vector used to encode a single vector. Okay, now given this information, it has been shown that any decoder model or any standard decoder model is going to have these many number of parameters. So 12 into the number of layers into D square model. Fine. So okay, so in case of GPT-3, which is said to have 175 billion parameters, it has 96 layers, and the D model was this. Right. Just input these values here and see whether you get 175 billion parameters or not. Right. So whether this is GPT-3, it is Llama, it is some other model, right? You just have to fill in the number of layers and D model for that, and you can estimate the number of parameters that particular model has. Okay, it's just that simple formula. Okay, now this is again true for any kind of a transformer model, right? So I've done it for GPT-3. You can do it for other models also, right? Again, this is a very standard formula. Now this is the total number of parameters. When I say number of parameters, these are the number of weights which are going to be trained in the training stage of the model. Okay, these are those trainable parameters. Fine. Now when I talk about total compute, so total compute means total number of floating point operations that you are going to perform, right? It is 6 into total number of parameters into total number of tokens. Right, again, this is true for any standard transformer model. So 6 into P, which is P is the total number of parameters, and D is the total number of tokens. Fine. Why 6PD? So again, there is an explanation. Whenever for each token in the forward pass, each weight will undergo one addition operation and one multiplication operation, and when you will back propagate, it is going to perform double of that, right? That means 2 addition and 2 multiplication. So that's why it is 6 operations per parameter for each token. That's why it is 6PD. Right. Again, you see the transformer architecture, it is kind of very kind of clear that why it is 6PD. Fine. And this is compute. So that means these are the floating point operations. Floating point operations. That those are required. Fine. To train a model. Okay. So what do we need? The amount of total compute used during training, example, number of training steps. Right. So this is a total amount of compute that is required to train a model during the training step. So maybe we always say like this, right? That maybe our corpus has 6 billion tokens, right? And we have maybe 1.3 billion parameter model. Then what is the total number of floating point operations that will be required to train this model? Okay, that is what this total compute is for. Fine. I'll give you some more idea, right? So there is this idea of flops, floating point operations per second, and then there is this very new term which has come last 3-4 years. This is called petaflop days. Okay, so there is this very specific, again very popular GPU which is called A100 GPU from NVIDIA, Ampere series GPU from NVIDIA. This is called A100. Okay, and NVIDIA claims that it can perform these many teraflop operations per second, 312 teraflop operations per second. Okay, so what is teraflop? It is 10 to the power 12 flops. A single A100 GPU can perform 312 into 10 to the power 12 floating point operations per second. Okay, and you can simply you can just write it like this, right? 3.2 or just 3 into 10 to the power 14 floating point operations per second, right? If I kind of multiply this number with 24 into 60 into 60, what does this become? The total number of floating point operations A100 GPU does in how many days? In a single day, right? In 24 hours. Okay, and if you do that, it is going to become this much: 2.7 10 to the power 19 floating point operations per day. Fine. Okay, now this is the total number of operations done by a single A100 GPU chip in a day. Okay, now let us talk about petaflop. So this was teraflop. Teraflop was 10 to the power 12. Petaflop is 10 to the power 50. Okay, now what is a petaflop day? So that means you perform this petaflop operations for an entire day. All right, so you have 10 to the power 15 floating point operations per second. You multiply this with 24 hours, 60 minutes, 60 seconds, right? And whatever it gives you, these are the total PF day number of operations that are performed in a day, right? And if you do this, this becomes, it is 8.6 e to the power 19 and 19 floating point operations per day, right? If you compare this with this, that means if I'm talking about PF day as a metric, it is almost equal to 3 A100 GPUs running the entire day. Now, just tell me if you have any doubts here, because again, the rest of the slides will be dependent on this PF day a lot. Are these metrics now clear?
Sir, is this our assumption that we are going to utilize the GPU completely while we are like calculating these? Because it's possible that even though we come up with some compute number, like we are not maybe utilizing the GPU 200%, or maybe there is some latency in communication or something like that, right?
Yes, I agree. So these are the best numbers, right? This is what is kind of so whenever NVIDIA or any company releases their GPU, this is the best performance that a GPU can perform, right? Or can do. But this is never achieved in the real experiments.
Okay.
Okay. So whenever we talk about compute, so this is the ideal scenario. This is the ideal scenario. Okay, that so suppose if you are estimating that we have to perform maybe 10 billion floating point operations, and our estimate gives that maybe we are going to do this 10 billion floating point operations in maybe next 5 days. Ideally it will take maybe more than 1 day or 2 days, right? So it will get complete in 6 days or 7 days, because again there are a lot of latencies are there. There is a lot of other issues that can happen. Again, the GPU doesn't run at that efficient the way it has been kind of produced for, or the numbers are kind of created for that GPU. Okay, so these are the real issues, right? But the overall, whatever we say, this is the total number of floating point operations which are there in one PF day. That we should remember. Whether a GPU is able to give these number of operations, that's a different thing. Fine, is that okay? I hope now the definitions are at least clear.
Yes, sir.
Okay, fine. Any other question you have, let me know before I move to the next slide. Okay, Fine. So I hope PF day is now clear, right? Okay, and we are also clear with the these two formulas. One is for total number of parameters in a transformer model, and total compute that is required to train a transformer model with a specific number of parameters and a specific data set size. Okay. So now the question is the following: that suppose we want to train a model, right? Then how should we scale it? Scale it means how should we train that model on a very large data set, maybe, or a very large architecture, right? So ideally, whenever we want to train a model, what should we pick as the optimal model size? What should we pick as an optimal data set size? And what should be the amount of total compute that can be used during the training, the optimal one? Okay, so this is what we are going to talk about here, right? So again, the big picture is this one. Given a fixed compute budget, what is the optimal model size and the training dataset size for training a transformer language? When I say compute budget, what does this mean? Maybe I give you beforehand that, see, you can only perform these many numbers of floating point operations. Okay, now given this compute power, what should be your model size and what should be your optimal data set size so that you receive the least error or the least loss, right? Again, I've not defined loss or error till now, but this is what we want. Okay, and we will pick those, the optimal model size and the training data size based on some estimation that we're going to see now. Okay, now suppose the question is this, that again, the same question in a more kind of more intuitive way. So given you are given a GPU for a day, right? Some GPU, it is not A100, it could be B100 also, it could be A100, it could be H100, any GPU for a day, right? Then the questions are this following, that would you train a 5 million parameter language model on 100 books, or you are going to train 100 million parameter language model on one book, right? Or 100K parameter language model on 500 books, 5K books, right? Again, these are different settings, right? These are different settings. Okay, now if you see, the compute in all these three is exactly the same. The compute in all these different settings is exactly the same, the total compute, right? But what is the thing that we are varying? The parameters and the data set size. That is what we are varying, right? The compute is still the same. Fine. Any questions till here? Because this intuition we are going to use next. No? Okay, great.
Sir,
Yes.
sir, would be the performance different for all the three variations?
So this is no. So that is what we are going to look into. That
Okay.
which is going to be the best, which is going to be the most optimal setting.
Okay.
Right. That is why we are going to propose these scaling laws. Okay. So idea is your compute is fixed, right? Now you can vary the dataset size, or you can vary the parameters, the model parameters, right? And you have to pick that particular setting of the model size and the parameter which gives you the best results for that given compute. Fine, is that clear now? And we will see that how to do it next. Okay, so this was the first paper which came from OpenAI in 2020, Kaplan et al. Right? And there they actually introduced the scaling laws for large language models. So what they said is the following. Again, these are some very interesting insights. That performance of a large language model depends strongly on the scale. And when I say scale, it depends on the model parameters, the dataset size in number of tokens, and the compute used for the training. So what they say is the following, that the performance of a large language models depends only on these three things. But it depends very weakly on the model's shape. That means depth and width. So what it says the following, again, people who know transformers, right? What it says the following, it doesn't matter if your attention heads are less and your D model is larger, or your D model is larger, attention heads are, or D model is small, the attention heads are more. right? Or it also doesn't matter if your if kind of your that uh, uh, these total number of attention head, and this one is one thing, then maybe you can also have the variations in uh, the feed forward layers, right? So again, those are larger in size or the smaller in size, that doesn't matter. What matters is the total number parameters the model has, the architecture has, the total size with which that is going to be trained, and the total compute which is going to be used for training. Is the architecture, the specific insights in the architecture, the specific components in the architecture, they do not matter much. Okay, this is what these people have said in 2020. Okay, another thing which they said is the following. Then these three are three different scaling attributes. This is attribute 1, model parameter. This is attribute 2, right? And this is attribute 3. Right. Now they are saying that performance versus scaling attributes can be modeled using power law. Okay, so what is the power law? How does the functional form of the power law looks like? So when you say y equal to x, or y equal to maybe y equal to mx plus c, what does this functional form looks like? It looks like a line, right? Then you might have seen this form also, y equal to ax square. What does this looks like?
Parabola.
Parabola. Okay, fine. So what it says is the following, that we are looking into this kind of functional form, where a and b are some constants, right? And when you are going to plot this, they are going to look like this, somewhat look something like this. Okay, fine. This is the idea here. Now you can write it like this, that a x to the power minus b, and this b is the exponent of this power law. Okay, power law, the idea is the following, that for some x, the value of y is going to be very high. For most of the x, the value of y is going to be very less, right? So this is true with the way the money is distributed among humans, right? So 80% of the money lies with 20% of the people, right? The rest of the 20% money lies with the 80% of the people. Okay, so that is again a very intuitive form of a power law, and that is what this power law looks like. So what they are saying here is the following, that performance versus scale can be modeled using power laws. All these model parameters and their performance that you're going to get will be modeled using power law. So their dependency is the functional form that they follow is the power law distribution. We'll see that. Okay, this third point is again very important. Performance improve most if the model size and dataset size are scaled up together. Increasing one while keeping the other fixed lead to diminishing returns. So what it says is the following, that suppose in the beginning you have maybe C as the compute. Maybe C is some number of floating point operations that are allowed to do. Okay, then suppose you got some more GPUs, right? And your total compute that now you can support is going from maybe from C to 4C, right? Now that there are two options, there are three options. One option is you only increase the size of your model, you increase the parameter size, right? Or you kind of increase the parameter size. The other option is you increase the dataset size. The third option is you increase your parameter size also of the model, and you increase the dataset size also, right? And this is where this is the performance improvements are maximum when both model size and dataset size are scaled up together. Increasing just one while keeping the other fixed will lead to poor results. Is this line clear now? Fine. Okay. Now the last one. larger models are more sample efficient than smaller models. They take fewer steps, data point to reach the same loss. Right. So now suppose you have a model, maybe you have a model which is 8 billion parameter model, and another model is just 1 billion parameter model. Fine. These are two different models. One is bigger model. This one is a smaller model. Now you are passing maybe 1K instances here to train this model, and 1K instances here to train this model. Okay. So this model, the bigger model, will be trained better with the same 1K instances than the smaller model with the same 1K instances. That's what this slide says. Larger models are more sample efficient than smaller models. They take fewer steps, data points to reach the same loss. We'll see some plots that will make the life more easy. But that is what these 4 lines. Again, this is just the crux of this entire paper. We'll see plots now. Okay, let us start maybe looking into this parameter plot. Okay, so the parameter plot here is this. What it says the following: we have trained models with different parameter sizes. Okay, we have trained models with different parameter sizes. Okay, keeping what same? Keeping the data set size same. So this time data set size is same, number of tokens are same, but we are training with larger and larger models. Okay, so this is a model with a 10 to the power 5 parameter. This is a model with 10 to the power 7 parameter. This is a model with 10 to the power 9 parameters. Okay, now if you see, as we are increasing the model size, the total loss is getting reduced. So it started from here, it is getting reduced. Fine. So, and the idea here is you are increasing the number of parameters of the model, keeping the data set size same, right? So what do you think? Your compute is increasing with the time as you are increasing the total number of parameters of the model? What do you think?
It should increase.
It should increase, right? So again here, in order to create this plot, compute is not constraint, right? So compute will increase as you are increasing the total number of parameters, keeping the data set size same, right? But the idea here is, as you are increasing the number of parameters, you are seeing that the total loss is decreasing. The total test loss is decreasing. Fine. So if you see this, the functional form that I showed you here, this one, y equal to a x b, right? If I take log on both sides, log of y, then it will become log of a on the right side minus b log of x. Fine. So what does this now becomes? If I plot it on a log axis, it is a straight line, right? So if you see these plots, all these plots are in a log axis, right? And if you see, this actually is a straight line. The functional form is this one. Y is the loss, y is the loss, right? And this all this is on the right side, right? So this is that a by x to the power b. Exponent here is 0.076. Okay, value of a is 8.8 into 10 to the power 13, and so and so, right? So again, you just convert this formula into the log scale, plot it, it is going to be the straight line. Okay, now let us see for the same thing for the data set size, the middle one. As you are increasing your data set size from 10 to the power 8 tokens to 10 to the power 9 tokens, see, the loss is decreasing. Fine. This time, if you plot the same with loss with respect to your data set size, the exponent is 0.095. Okay. And then the same thing you can do with your compute also. Right. So here the compute is in terms of petaflop days. Right? The way I define the petaflop. right? So these are the petaflop amount of compute on which are on the x-axis, right? And then on the y-axis, it is again the loss. Okay, and here we are plotting what? We are plotting the training profile of different models. So each line corresponds to one model. Each of this line corresponds to the training profile of a one model, right? And if you see the minimum loss that each, so how does this training works? The test loss works. Your loss will increase, the loss will decrease over the time. It will decrease over the time. It will become stable after some time and then starts increasing, right? Now the minima of all these curves, if you see, lies on this line. The minimum loss that you can achieve that is achievable by a model lies on a straight line for different settings, right? So for each setting, you have some number of parameters, you have some data set size, right? You train a model on that, keep it training, and you are going to get a curve like this. So this curve is time or maybe number of iterations over the time, and y-axis is going to be your test loss, right? So that's why you have these many number of curves here. But the minima is going for all these curves will form a very nice straight line. Fine. Now one more question here. Why we have so many curves here? Why we have so many curves here? Whereas we have some very less number of points here. Because for a single compute, we can have different settings of P and D. For a single compute, so compute could be maybe I can only give you some number of floating point operations, right? Then you can have different value of P, and you can train a model with different P and different D, right? And then those will be different. Each P and D becomes one model type of training, and you can have many such training for a single compute. That's why you have so many curves here, right? But the idea here is all these curves, the minimum loss that you are going to get is going to be present on this nice straight line. Fine, and that is what this paper was kind of popular for. Okay, this is another very interesting figure that was present in this paper. What it says the following. Okay, so let us just first read this left figure here. You have these yellow color lines for bigger models, and then you have this blue purple color lines for the smaller models. Okay, and you are passing the tokens. So x-axis, you have the total number of tokens. So we are increasing the total number of tokens. That means we are increasing the total data set size. Okay, now as you are increasing the data set size, your loss is decreasing. That we have seen before also, right? The loss is decreasing. But for smaller models, in the beginning, the loss decreases, then it's just plateaus. Fine. Whereas it doesn't happen if your models are bigger, right? So in this case, the yellow one, right? So here, if you see, as you are adding more and more data, your the test loss is still decreasing. Okay, so this is again very interesting kind of observation by training large number of models with different parameter sizes. Okay, so smaller models will tend to saturate very fast. So even if your data set size is huge, you might not get that performance as you're getting on a bigger model with the same data set size. Okay, one more thing is this, that larger models require fewer samples to reach the same performance. Okay, suppose we are talking about this particular performance, a test loss of 6. Test loss of 6, right? Now, a model with a 10 to power 9 parameters will only require this many number of samples. Where a model, maybe the smaller one, will require a very large number of parameters or very large number of tokens, data sets size. Or maybe we can see here, suppose I want to get a test loss of 8, we will require this many number of tokens, right? To get the same test loss for the smallest model that I have, I need to feed these many number of data sets, these many number of tokens in the data set, right? So larger models, they require fewer samples to reach the same performance. Fine. Another plot. See this plot. Again, here it is same. These are the smaller models. These are the larger models. So this is 10 to the power 9. This is 10 to the power 3 parameter model. And on x-axis, you have the compute. Fine. Okay. Now what it says the following. As you are increasing the compute, okay, whatever you do, the model performance of the small models is going to saturate. They're not going to do better, even if you increase more GPU and whatever you want to do, right? But the model performance will not increase. It will get stable at some point, right? Whereas if you have the bigger models, as you increase the total compute, they will become better and better over the time. Fine. Now what it says is one more interesting thing. See this particular area here. What they say is for the bigger models or for any sort of models, it is not kind of mandatory that you have to train the model till it reaches the minimum loss, right? Because that might take a lot of time. So it is okay if you can stop it before also. So that's what this line says. Compute efficient training stops far short of convergence, right? So don't wait for the convergence. That, see, I'm start training my model. I'll only stop training it when I receive this the lowest loss, right? It might take years to get that particular loss. So it is okay. You can stop here also. It's fine. Whatever the idea is, that the loss here and the loss here, again, this is not going to be very, the difference is not going to be huge. So it is okay to stop here, because then you will be saving a lot of time. Okay, these are some of the very interesting observations from this paper. Now, before I move to the next slide, let me know if you have any questions in these two slides. Again, these are the important slides.
Have they mentioned which exact component is causing this issue? I mean, for the smaller models, it's saturating quickly.
No, so they have not done any analysis at the architecture level.
Okay, got it.
Okay, so what they are saying is architectural level specification doesn't matter much. What matters is the overall size of the model.
So it might be because of the attention weight matrices or the feed-forward network weight matrices, something
It
like
could be anything. It could be anything. Yes, yes. But in general, they achieve these kind of results. Yes.
that. Okay.
Any other question? Let me know if you are not able to get anything. So before I move to the next slide, if something is not clear, that also you tell me. So I'll make it clear. Fine. Okay. So then there were some issues with this, with the laws which were proposed by this OpenAI paper. One of the issue was the following, and again, this was the major issue that was pointed by a lot of people later, that for all the experiments that they have done, they have used the same learning rate schedule. So whether you are training your model for smaller data or you are training your model for the longer data, for the larger data, right? They have kept the same learning rate schedule. So learning rate schedule is the following, that as you are training your model, there is a parameter, there is a hyperparameter learning rate. Right. So there is a parameter, hyperparameter called learning rate, right? And which decides how fast you want to train your model. Okay. So over the time, what people do is the following, that they will increase this learning rate to maybe some maximum value. Then they will start decreasing it and then maybe over the time it becomes kind of a stable, right? This is a learning rate. Okay, now for all their and how they do it, maybe for the first 1000 batches of the data, they are going to pick LR equal to maybe 10 to the power some value, the 10 to power maybe -6, right? And then maybe for the next 10 batches it could be this much value, for the next 100 batches it could be something like this value, right? Overall the plot looks like this. So the idea is, in this paper they have not experimented by changing the learning rate schedule for different dataset sizes. Okay, it remained same. Okay, so what could have been happened is, if suppose you are training a data, if you are supposed training a model on smaller data, right, it is fine. But if you're training a model on a larger data, for most of the batches your learning rate could have been very less, right? So there was not a proper training that was happened on those batches. Okay, so this was the major issue that was pointed by a lot of people once this paper came out. So the schedule need to be adjusted based on the number of training steps, otherwise it can impair performance. It happened actually, right? And one of the reason why the scaling laws which was shown by Kaplan et al, this paper, were flawed. Okay, then in 2022, 2 years later, this paper came. This was called Chinchilla paper. All right, it came from DeepMind. So this is after 2 years, right? What they have said is the following, and again the kind of the major differences between the two papers is the following. So this is our OpenAI paper, and this is DeepMind paper. Right. In OpenAI paper, what they said is the following: if you are able to increase your compute budget, you should prioritize increasing model size over data size. That's what OpenAI people said, right? So suppose if your compute is increased, then what ideally you should do? Ideally, you should increase both, right? You should increase your dataset size also. You should increase your model size also, right? But which should be prioritized? They said that the model size should be prioritized over the dataset size. Fine. So what it says is the following: if suppose we have a 10x compute increase, then you should increase your model size by 5x and dataset size by 2x. Right? If you have a kind of a 100x compute increase, then maybe you increase your model size by 5x and dataset size by 4x. Fine. This is what OpenAI paper said. Okay, and how does these values comes from? These values actually are coming from these exponents. Okay, so these values are coming from these exponents. What does this DeepMind paper said? You should increase model size and dataset size at the same rate. Okay, so with a 10%, if suppose your 10 times compute is increased, then you should increase your model size as well as dataset size by 3.1x. Okay, if it is 100x compute increase, then you increase both model and data size by 10x. Remember, all these are rates. These are not exact values. It is not the case that if the number of parameters are, you have to keep the number of parameters as exactly the number of tokens in the dataset size. It is the increase that we are talking about. Whatever your base model is, if you are getting 10x compute, you increase the both model and dataset by 10x, whatever the base value was. Okay, so this was the plot. Again, very similar plot that was created before, but this time what they are showing is the following. See the x-axis. X-axis is the total number of parameters. Y-axis is the loss, right? So they use test loss. They in this paper they are talking about training loss. What they have done is they have kind of approximated the test loss using the training loss, right? And one of the reason why they have used the training loss is because for each of the model, for all the models, they have not even trained for one epoch. So that's why they are not even calculating those test losses. They are just showing the training losses. Okay, so y-axis is loss, training loss. Y-axis is training loss, and x-axis is number of parameters. each color here represents same compute, right? So this is one compute, this is another compute. When I say compute, so these are the number of floating point operations, right? So these are the floating point operations for this curve. These are the total number of floating point operations for this curve. These are the floating point operations for this curve, and so on and so forth as we come down. Okay, so and this is how the models were trained. Okay, now let us talk about this particular first curve here. Okay, so if I fix the compute here for all these dots, if I fix the compute and I increase the total number of parameters, what will decrease? So if I fix my compute and I'm increasing the total number of parameters, what will decrease? Anyone wants to try? So see, when I say I fix the compute, that is my model is going to do this many number of floating point operations. Okay, what was the formula for compute? It was 6PD. My compute is fixed. Now I'm saying I'm going to increase the parameters. So what is the other variable which I have to decrease now?
Dataset size.
Dataset size. Okay, so if you see these beads, this is bead 1, bead 2, bead 3, bead 4, and so on and so forth, right? What you are trying to do is, so this particular setting, this particular model was trained with the least number of parameters, but the highest number of tokens for the same compute. Whereas if I see this particular bead, this was trained with the highest number of parameters, least number of tokens for the same compute. Is this setting clear? And same goes for all the different colors as you go down. Now the observation here is the following. As you are increasing your parameters, right? It is not the case that every time whenever you are increasing your parameter size, the model is going to give you the least or the lesser loss, right? So it is going to go down to some extent. It will reach the minimum loss that it can get, and then again the loss will start increasing. I hope this makes sense, right? So as for a given fixed parameter, for a given fixed compute, as you are increasing the parameter size, it is not the case that you will get lower and lower training loss, right? The training loss will decrease to a given point, reach the minima, and then it will start increasing. Okay.
What about learning rate?
What about
Learning rate.
learning rate? They have managed the learning rate here. Yes, the way they have done the experiment, it was done based on the token size. They have changed the learning rate schedules.
Okay.
Okay, so this is again a very nice observation that they were providing here, that you are going to get minima somewhere in between. And when I say in between, so in between the maximum parameter and the minimum data set, and the maximum data set and the minimum parameter. So it is going to be in between. Now, as we go down, as we are coming down, if I see this particular curve, okay, so here also you are getting maybe the minima somewhere here. Maybe this could be the point where you are getting the minima. Okay, so as you are increasing your compute from here to here, one thing which is guaranteed is the following, that you are going to get lesser and the lesser loss, right? But one thing which is not guaranteed is the following, that as you are increasing or as you are keeping your compute fixed just by increasing the parameters, but just by increasing the size of your model will always give you the least loss. Fine. This is the nice observation made in the Chinchilla paper. Let me know if you have any questions here. No? Okay, fine. They did the same thing here this time. What they are doing is the following. They are picking these points, the points for which you are getting the least loss. The points for a given compute, what is the data set size, and what is the optimal data set size, and what is the optimal number of parameters. When I say optimal, that setting which gives me the lowest loss. Okay, and the plots that they have created are like this. So this is the parameters, this is the compute for a given compute, and this is the parameters. They just put all the points for which they got they just kind of calculated for all the floating for all the compute ones. So this is like for one compute setting 1, this is compute setting 2, this is compute setting 3, this is 4, 5, 6, 7, 8, 9, right? For each of these compute settings, they have created these two plots, right? So one, they are finding the optimal parameter for that particular compute setting, and they just plotted like this. If you see here, what does this, all these points are coming into? They are coming into a straight line, right? Same thing, you do it for tokens. All these points are also coming into a straight line. Now, what if I extrapolate, right? So suppose I have maybe I'm suppose here, I have total floating point operations around 24. I want to find out that what is going to be the optimal parameter size for which I should get the least loss, right? So I'll just go up on this particular line. I'll pick the total number of parameters which are going to be points, which is going to be 63 billion, right? Same thing I can do here also. Suppose my fixed compute cost is 10 to the power 24. I want to find out what is my optimal dataset size, which is going to give me the least loss, right? I'll come here, right? It is going to be 1.4 trillion tokens. Any questions here? And that's how you have to take the decisions. Okay, so the power law equation that they have proposed the following. So the loss is in terms of these two variables. N is the number of parameters. We were earlier calling this as P. Again, this is same. And D is the total number of tokens in the data set. All right, so your loss is in terms of these two parameters, N and D. Okay, so how do you define? So function somewhat looks like this, right? I'll explain how to find out the optimal set of parameters. So it is kind of a optimization equation. So you can write it like this: arg min of L n comma D. So we have to find out the minimum loss, right? And we have to find those arguments N and D, right? So N and D such that flops N and D is constant, right? So what we have to do is the following. We have to find out the minimum loss for a fixed compute, right? So we have to find out the minimum loss for a fixed compute, right? And then we will just return those N and D. And the loss is defined like this. They have defined it like this. You can say why this, but this is how they have defined it. Okay. And what is this E? So what they say is the following. Suppose you have infinite amount of data and you have infinite amount of compute. Okay, so if you have infinite amount of compute, what will this particular component will become? If you have infinite amount of compute, infinite amount or I should say infinite number of parameters, then what will this particular value become? 0.
0.
Right. If you have infinite amount of data to train on, this will also become 0.
Yes.
Right. Then what is E? E is the minimum loss that you can achieve when you have infinitely large parameterized model and infinite amount of data available. The best loss that you can achieve, that is your E is. Is this clear? What E is? Like what is the intuition behind E?
Sir, how they got this 1.69 equal to 1.69?
Just wait. So that I'm not
Okay.
yet explained. I'll
Okay.
explain that.
Okay.
Right. But I'm just trying to give you the intuition behind this this expression that they have created.
Yeah.
So this is just for a training loss or test loss?
So what they have done in their experiment is they have shown all the experiments for the training loss.
And this
Yes, this is all training loss. Yes, and they have approximated. They have shown that this training loss linearly varies with the test loss. So again, whatever observations are made here for the training loss, they also hold true for the test loss.
okay.
Fine. Okay. So if you see here, there are three components in this formula. One component is power law with respect to the number of parameters. One component is the power law with respect to the number of tokens in the dataset size. And one is with respect to E. What is E? E is the maximum, E is the minimum achievable loss when you have, and when this minimum is possible, when you have infinitely large possible parameterized model and you have kind of a infinite amount of data available for training. Okay, so you cannot achieve less than this. Okay, now since infinite is something which is not possible, right, you are going to get more loss, right? So this is the amount of loss which is introduced by having finite parameterized model, and this is the loss which is added to E when you have a finite amount of data, because you don't have infinite amount of data. So this is the loss which will come from the dataset size. This is the loss which will come from the model size. Okay, all these three components are going to come as part of my training loss. Fine. What they have done is the following. Yes.
So even for this like new updated equation, will the 6 PD loss still hold or is it going to look different?
6 PD loss, that was not loss.
No,
6
sorry,
PD.
compute.
No,
So
the compute is same. So if you see the way we are minimizing this loss is the following, that we have fixed our compute. What we are varying is N and D.
okay, so that 6 C equals to 6 PD will still hold it.
Yes, it will hold true. Yes.
Okay.
Yes, it is hold true. Fine. Okay. Now they have done they have ran a lot of kind of models. They have trained a lot of models with different C values, right? And they have varied the N and the D values. And finally, they have got the different constant in this formula as this. The alpha was 0.34, beta was 0.28, A and B were approximately 400. One was, I think, 406, one was 402. And then this E was 1.69. Okay, so E 1.69 means that this is the minimum loss that you are going to achieve. You cannot achieve better than that. Okay, and then they have then do a lot of things. What they have done is the following: given a fixed compute budget, what is the optimal model size and the training data set size for training a transformer language model? This is what we started our slides with. Okay, they experimented with lot of models which were proposed before this work. Okay, and all these models, it was shown that even though they were very big models, all these models have more than 100 billion parameters, right? So this was 137, Lambda was 137. This was by Google, and then GPT-3 was from OpenAI, right? 175 billion parameter model, right? Gopher, I think, was again by DeepMind. This MTNLG was from Microsoft. Jurassic is something I'm not sure, but where it came from. But this MTNLG, so this came from Microsoft Turing team, right? And see the size. All these were very, very large language models, and the data set size. So this was 137 billion model, 168 billion training tokens. 175 billion model trained on 300 billion tokens. 178 billion model, 300 billion tokens. 280, 300, 530, 270. One of the strange thing which happened with this model is, so here if you see, the number of tokens are lesser than the number of parameters. And this was one of the reason why all these models performed very poorly. The Chinchilla paper, the Chinchilla model that was proposed as part of, or that was proposed immediately after this scaling law, said that we trained a model with 70 billion parameters, a very small model compared to all of these, on 1.4 trillion tokens. And the performance was better than all these models. Fine. So this was again another plot which was created by the same set of authors. What they said was the following. So this plot is between flops versus parameters. All right. So you are increasing the total number of floating point operations. You are increasing your compute, and then you are seeing the total number of optimal parameters. Okay. What they have said is the following: the the 3 stars here. One is Gopher, one is GPT-3, one is Megaton training. This is from DeepMind, the same authors which proposed this Chinchilla model. GPT-3 is from OpenAI, and this is from Microsoft. Very large models, right? So the scaling here is happening in this way, that as you are increasing your compute, you are investing your compute more on the parameters than on the dataset size. Right, and this is one of the reason why their performance or the output that was expected was lesser than what we got from the Chinchilla model, right? So in case of Chinchilla, if you see, it exists somewhere here. So here, as you are increasing your compute, right, you are equally kind of increasing both the total parameters also, the dataset size also. Fine. One more thing they did. So this was one this formula was proposed. This power law equation was proposed by Chinchilla people. They also compared with the formula that was proposed by the first paper, the Kaplan et al. Right. In Kaplan et al, what they said is the coefficient for optimal number of parameters is 0.73, and the coefficient for optimal data set size was 0.7. In this paper, they said it is almost 7. It is almost equal. 0.5 for optimal parameters also, 0.5 for optimal data set size also. And these are different methods which were used to estimate these coefficients A and B. All right. So, but whatever models and whatever methods they have used for this estimation of this alpha and for this A and B, the values were almost same. Whereas in Kaplan et al, the OpenAI, they said that for n, for A, for n, optimal n is much higher, almost 4 times than what you see for data size, right? So if you are getting your 4x kind of increase in your uh, compute, then you are going to give more. You are going to increase your parameter size more than what you're going to do for your data size. Okay, fine. Again, they created another. They showed another table that if your parameter size is this much, right, and you have, then ideal is that you take this many number of tokens, right? So if your parameters are this many, the ideal number of tokens is this much. If your parameter is this much, your ideal is this one, given this particular flops. Fine. So that's what was kind of talked about in these two papers. Then there was a very interesting paper which came later. Again, so there's some problem with this last slide. I'll just explain what it says. The following: that even though both of these papers have talked about the total number of parameters and the amount of data set that is required to train and to get the optimal settings, right? It was not, they were not talking anything about the type of the data. Okay, now when I say type of the data, so the idea here is the following: most of the internet data is very noisy, right? So it might can contain text from a lot of social media handles, right? It might can contain text from poetry, prose, and all this kind of thing, right? So it is very noisy. Lot of issues are there. So that's what this says, that internet contains a huge amount of text, but it is extremely noisy. Whereas the copyrighted text, for example, the published books, are much higher quality, but it is legal to train on them, right? So is it even legal to train on them? That's what it says. So what it says is the following: suppose I pick one word from Twitter and I pick one word from any of the book, right? Any of the very popular book, or kind of the books which are present in a digital form, right? The information present in the token will be much higher for the book than for the same token present in a social media handle, right? So if you are going to train something on that particular text, you are not going to gain much, whereas you are going to gain much if you train on data which is copyrighted or which is behind the paywalls, mostly because this is a very high quality written text. Okay, so this is again the problem, right? Now, but getting that data is very difficult. Getting data which is copyrighted, which is behind the paywall, and it is kind of impossible to get that data. Okay, so at the end, what is left with is you have to train your data, you have to train your models on what? The noisy internet text. Okay, now what can be some problems? Some of the impacts of the repeated data. So we were talking about deduplication in the last set of, I think that was the last lecture, right? So why we wanted to do deduplication? So there was one experiment that was done. So what they have done is the following: they had this 800 million parameter model. Okay, now they trained it on some data, right? They do another training on the same model, but with some change in the data. So what they have done is the performance of the 800 parameter model can be degraded to that of the 2x small model by repeating 0.1 of the data 100 times, despite other 90% of the training data remain unique. Right, so they just retrained that same 800 parameter model again on another data set where 90% of this new data is same as before. The 10% of the data, what they have done is they have just used 0.1% of that 10% and they have repeated it 100 times. Now they are training this on this new data, the same model, and the performance degraded to a model which was half of the size. Right, so there is a kind of a very strong performance decay if you are training your model on the duplicated data. Okay, and that is the reason why we should deduplicate our data sets. Otherwise, the model performance will be heavily impacted. Okay, same
Yes.
experiment was done same year 2022 This was done by, I think this was done by Facebook team, Facebook research. They released this model called Galactica. What they have done is, they have 100 GB of scientific data. They trained their model on 100 GB of the data 4 times. That means for 4 epochs. Right. What they have said is, after 4 epochs, that means they trained their model for first 100 GB data, then they have reused that 100 GB data again, trained the model again on that, again trained on that, again trained on that, 4 times. Okay. What they have said is the following, that even though we repeated the data 4 times, the performance gains were huge, which is contrary to what was proposed here.
But
Right.
that was the
Yes.
that was the epoch, and in this case they have telling about the duplication. So duplication will be in, for example, in a one epoch, they will get 100 times the same data point,
Yes. 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 You are agreed.
and
Yes.
the Microsoft have done the epoch. I mean, has
So they
only
have
one
done four
single.
times. Maybe this time. So here, maybe if they have trained it for 1 epoch, they have done it for 100 times, right? In case of Microsoft, in case of Facebook, they have done it for 4 times. That's the difference, right?
Yes, and along with that, the I mean, the data they have has I mean, are different. All the data they are, I mean, model is learning different data, not the same
Yes,
data.
yes, and that is where the answer is, right? So this model was trained on mostly on the internet data, right? And this was this Galactica model. This was trained on scientific data, right? So the data quality was very significantly different in both of these two types of data set. So what it has been said is the following. Even so, if you perform repetitions, if you perform deduplications, if you kind of take a duplicated data, but the data quality is very good, the model performance will always mostly increase, right? Whereas if you use a noisy data and then you further don't deduplicate it and you are training it on that duplicated data, your performance will degrade over the time. Okay, again, there are a few more papers by OpenAI where they have said that, then again, not just by OpenAI, by different researchers, where they have said that what is the optimal data that you can use. Again, this data is very high quality data, which can give you similar performance than the noisy data which you get from the internet. Okay, so the scale is huge. The difference in the scale is huge, right? But creating that good quality data is very difficult challenge, something which is not kind of possible. Okay, so that is one of the reason why most of these models are trained on internet data. Okay, this is where OpenAI has done the major work. They have trained the data. They have created the data which is of very high quality by kind of recruiting people, paying them very well, creating manual data sets. Okay, so that's all for today. Okay, and this is what I just wanted to discuss, the scaling laws. Yeah.
So for the second part, that is not essentially a repetition, right? Because whenever we are training any sort of LM, we will be training it for more than one epoch, right?
This is not true, Shruti. So if so, usually it has been said that if your data set is huge, people don't even do 1 epoch training.
Even
So
for the larger LLMs.
yeah, larger LLM, see, if you have huge resource, you can always do it, but it is not even recommended that you kind of train it till the convergence. And you can get a convergence even before 1 epoch if your data set size is huge.
Mm-hmm.
Right.
Achha.
So in case of Chinchilla paper, they have done experiments with so many models, but they have not trained even a single model for one epoch.
Mm-hmm. Okay. And also, like, I mean, there could be some other reason why Galactica model is like very bad, but
Yeah, that is always possible, but this is what the papers are talking about. There might be other reasons. Yes, equally possible. So again, all these people, at least these two papers and the subsequent papers which have come, they have explicitly said this thing that the scaling laws, whenever we are conducting experiments for the scaling laws, right? We have never seen any significant kind of impact of the architectural changes, right? Which could not be true, right? Right. But this is what has been said. And this maybe someone else might in future can refute this. No, these architectural changes might have a major impact, right? And this could have been one of the issue in case of Galactic also. Again, the training itself was very poor. We know that the training itself was very poor, but there might be other reasons also. Don't know.
And also, like Hitesh was last time discussing that, like deduplication of data, right? So that is also not the exact same copy, right? Or is it like deduplicating the exact same instances from the
No,
data?
so it is not exactly the same. So again, the threshold you have to define. So it's kind of the fuzzy similarity you're talking about.
Okay. And like I know like the entire presentation was about the scaling log, but so like what we have at the end is that compute is equal to 6 NBS equation, right? So whenever you want to start from scratch, we should ideally use that for estimating the model size and the parameters and the dataset size, right?
Yes. Yeah. Yes.
Okay. Okay, so thanks.
So we have not, so in this compute, we have not included the floating point operations required for your embedding matrix, because you also have this embedding matrix in the beginning and at the end, right? So that was not included in any of these papers. That the embedding matrix is fixed. That is not trainable.
Okay.
Okay. Any other question?
Sir, when we get that equal to 1.69, so does that mean for any model we cannot go below, we cannot achieve loss less than 1.69?
I think so. I'm not very sure, but this expression is in general, right, for all the models.
Okay.
Right. So there was no we have not seen any model specific kind of equation here. So this is in general. And that is the reason I think newer these models, these scaling laws have also come, right? I have not read those papers, but probably Shruti, if you have read those papers, you can shed more lights on that.
No, sir, I have also read only till Chinchilla.
So very recently, I think 2 months back, one more paper has come. It showed that it is refuting some of the claims made by Chinchilla, but I have not read that paper, so I don't know exactly what they're saying.
So, sir, which scaling laws should we follow? Like, so the one in general.
So in general, if you see Chinchilla, I think the way they have experimented and they have shown that for this case particularly, this table, right? This was actually making sense. That if you see all these models, they were very big, right, and trained on significantly lesser amount of data, and they were not performing very well. So the Chinchilla paper said one more thing, that see, you require smaller models to give similar amount of performance on similar to kind of the bigger ones. Okay, so this will do two things. One is that, see, not everyone has infinite kind of supply of GPUs. So we need to train smaller models. We ideally had to train smaller models. So in that case, this scaling law looks good, right? Another thing is, at the inference side also, if you have very large models, the inference time is also going to be higher. Okay, so it is good that maybe this. So ideally, I think most of the newer works are following this chinchilla work. I don't know if someone else is deviating from this. So, and these are the two major reasons why we should follow the chinchilla. Again, it has shown empirically it is better than what has been shown before, and then the reasons are also looking more realistic.
Sir.
Yes.
Sir, I was just like wondering, if we have a multi-models, let's say we have different modalities, so will it also stand true in that case? Because the number of parameters might be same. Matlab,
So it is not with respect to text language model,
right.
right? So it is not with respect to that. It is in general any language model.
Hmm.
If it is transformer based language model, that's all.
Hmm. Yes, okay, sir.
Also, given like now we have instruction tuning, so we are asking like teaching the same model different types of tasks and everything. So even in those cases, there could be a different scaling law, even for say techniques like RLHF.
Yes, possible. Yeah. See, RL is more sort of a fine-tuning technique, right? And all these models are, all these experiments are done on the pre-training side step.
I mean, I'm just thinking maybe that once we have done RLHF and like fine-tuned a model specifically for like certain certain aspects like safety or generating non-harmful content. In that particular setting, the exact same scaling law might not apply, because ideally the model has already learned that it should probably answer like that, but then we are doing an additional step of telling it that no, this is not preferred versus this is preferred.
Yes. Yes, possibly, but I think no one has talked about kind of. I think there was. I found one paper which was talking about scaling laws for fine-tuned models, but again, that was not very popular paper. So I have not read that. But at least the paper that we have covered and which have come subsequent to this are mostly talking about pre-training. And then their loss was also this cross entropy loss. So, and the task was next word prediction, simple decoders, this like self regressive to task. That is the task. Okay, fine. So I'll then end here. Hitesh, you are going to present next, right? In the afternoon.
Yes, sir.
Okay, fine. Okay, sure. Okay. Thank you, everyone.